So we were here before the break. The first thing we note is that in principle, as just explained, good question. In atoms other than hydrogen, the energy will depend on the single electron states. Energy will depend on two indices, N and L, all right? And therefore, schematically, for other atoms, it looks different from hydrogen. Hydrogen is a very special case. It only depends on N. It is accidental. It is due to the exact form of the Coulomb form. So it relies more. It depends on more information than central V of R. But for any V of R, we have the right-hand side. So here schematically, we have exaggerated just to show the feature. 2s and 2p, they have different energies. So are 3s, 3p, 3d, and so on. And in many cases, there will be crossing. By that I mean, here you see 4s is drawn slightly lower than 3d. And that is the case in filling up the periodic table. But let me remind you one more time, an important concept. Don't take one such picture, I mean this thing, don't take one such picture and use it for all atoms. That is not the right approach. Strictly speaking, every atom is a different quantum mechanics problem. Why? Simple answer. The Hamiltonians are different, right? Helium Hamiltonian, rather simple, 5 terms. Lithium Hamiltonian, many more terms, right? You have many more pairs of electron-electron repulsion, kinetic energy term, and also seeing the nuclear charge. The Hamiltonians are different. No reason why one picture can fit all. Okay? Be educated. Don't be too naive. Okay? So what you learn in general chemistry is just a very rough picture. So the following pages, let's do something very lazy and very simple. Okay? But rather physical. Good physics stuff here. So let's discuss on some general patterns of the energy levels within this independent particle approximation. So after we solve it, do we expect 2s to have a lower energy than 2p? If so, why? All right. So here is the some hand waving discussion. So 1s, we have this picture is closer to the nucleus. All the other electrons will not screen the nuclear charge, thereby it will see the whole nuclear charge. Roughly speaking, 1s will be of this energy. Okay. If you look at the numbers, I give you some table later on. It does. Roughly, it is the case. Then n equals 2, the principal number 2, then we know that they are not the same because not strictly Coulombic. And then which one will be lower? 2s is lower than 2p. Then physically, any hand waving reason that can be understood? Well, there's one way to do it. We think about the wave function. But then you say we don't know the wave function. We haven't solved it, right? Every atom is a different problem. Then when thinking about atomic physics, still the hydrogen set of wave function, which we can solve, the only case we can solve exactly will be very handy to help us think. The other atoms, of course, we need the numerical solution of the wave function, all right? But hydrogen, nevertheless, give us a very good concrete set of wave function with pictures to think about. So here I grab a hydrogen result and make the argument. What I plot here is something called the radial probability density. If you forgot what it is something like this. We have the radial part of the wave function. So 2s is 2, 0. 2p is 2, 1. All right. Times r squared, that will give us the radial probability density. Physically, it means the following. Start from the nucleus. Don't worry about angle anymore. You integrate over theta phi. Okay. As you go out from the nucleus, what is the probability of finding the electrons in this shell that are out a distant r away from the nucleus? Okay, so that is this function, what this function means. So here I grab some hydrogen result. The big bump here is the 1s, not our concern. So 2s is this one. 2p is this one, the solid one, okay? 2s is the dashed line down here. What I want to argue is that there is a bump closer to the nucleus, r equals 0 in 2s wave function. Thereby, the 2s electron on probability-wise will be closer to the nucleus, thereby sensing more attractive part of the potential. Attractive means more negative, so we expect 2s energy to be lower than 2p energy for this qualitative argument. We can do loop self-consistent calculation, it is the case, all right? So similarly, we can also argue that this is the sequence for the 3s, 3p, 3d states. So this is the big picture. We have yet to learn how to fill the electrons in because there is something called the Pauli exclusion principle that we need to discuss. In quantum mechanics, Pauli exclusion principle can be viewed as a byproduct of a higher level requirement. The requirement has to do with the symmetry of the wave function, the many electron wave function, when we interchange two electrons. It turns out that nature required many electron wave functions to be anti-symmetric, off by a sign, a minus sign, when we interchange two electrons in the wave function. From that requirement, Pauli exclusion principle follows. We will do the discussion on the next set of notes after this, okay? So now I would like to backtrack again, back to where we were at the beginning of today's class, the Hartree fork thing, okay? And then I will show you some results of helium and the other atoms. So just remind you what we have done under the helium atom. This is the helium Hamiltonian. In atomic units, now I have an appendix post because if you are serious about atomic and molecular physics, then the atomic units are commonly used. So in atomic units, we measure distance by the Bohr radius, energy by Hartree, and then you can rewrite a rather complicated Hamiltonian to look slightly simpler. Or the charge is measured by the electron charge. So E is 1 unit, okay? So it's the same thing, same physics, of course, but in different units. And then at the beginning of today, we say we are looking for the ground state, one electron in some unknown 1s, another also in the unknown 1s, and then we have a self-consistent equation to solve, okay? So this can only be done in an iterative way, and then we can get the answer. Then after that, you get the best estimate single particle state. We are not done yet. If you want to get the ground state energy, you need to do an expectation value, all right, with the full helium Hamiltonian. So this thing is this thing, okay? After you do that, then you will get a number out to compare with the best value. So I give you I summarize what we just did in the beginning of today's class, all right? So now the problem is defined. There are many attempts in solving this problem in an iterative way, okay? Now, some lazy way will be, I take a function, I put in 1 or 2 parameters in there. So every time when I compare the output with the input, I adjust those 1 or 2 parameters until the convergence is achieved. Okay, so that is one solution to the Hartree approximation. Then another guy steps in. I will use 18 parameters in my trial wave function. So we believe that that must be a better attempt. All right, so one can try every method to solve this self-consistent problem. Then there will be so-called the best value within this method. That is to say, you try the most fancy wave function, okay? Many parameters to tune. That will be the best so-called Hartree-Fock limit. The meaning of it is that within this way of reducing a two-body problem into a single electron problem, this is as far as you can get, or as best you can get for the helium ground state energy. So here, I cite that value for you. So this is the very best one can do within solving this equation. The epsilon 1s is this. The Hartree limit of the ground state energy is this. Here, I also give you the actual value. This is the very best beyond Hartree or Hartree-Fock calculation, more serious than that, okay? And then it is not too bad, all right? But you cannot do anything better within our level of approximation. Here, I also give you another number to compare with this one as atomic energy. Here is the experimental value of the first ionization energy of helium. It is 0.9. So it is really not too bad in comparison with the ionization energy. And this leads us to another concept that I would like you to know. Again, there's no calculation that we can do here at our level. But I think some of you may want to go forward in condensed matter physics in your postgraduate study, etc. You better know these 2 pages, all right? So here I would like to define what is correlation energy. It's just a name, okay? So don't worry about the name at the moment. Now we know there are 2 things. For example, for helium, there is a actual value, there is a best value within this self-consistent field Hartree approach. So let's define the difference between the actual value and the best Hartree-Fock limit. So we notice this is the case in general. Then we can define the difference. The difference is called correlation energy. So it's the name, okay? Then physically, what does it mean? Remember, in our effective potential way of thinking, we are handling the Z-1 electron or the other electrons effect here by approximately that the other electrons are smeared out using the unknown wave function. Okay, so in order to account for the electron-electron repulsive term in the Hamiltonian, we make an approximation in the Hartree-Fock approximation. The difference here means that what is missing, not accounted for by this kind of averaged out the Z-1 electron effect. Okay? That difference, if big, we call this system is strongly correlated. If this correlation energy is small, meaning Hartree-Fock-like mean field thing is already very good, correlation energy is small, and we could say the correlation effect in that system is small. Okay, so in our example, correlation energy of helium, you subtract the two numbers, it's not big. Something like that. That should be compared with above 3 Hartree, right? 2.9. So 1%, something like that. Okay, so it's already good to 1%. So helium is not a strongly correlated system. But there's some funny thing in this definition. If you notice, the Hartree calculation, self-consistent or Hartree-Fock, I haven't defined what is Hartree-Fock for you. What is that Fock here? We need to wait a little bit. Then, but think about Hartree. That is an approximation. The funny thing is that in order to define the correlation energy, we need to intentionally do a wrong calculation, do an approximation in order to get the difference. That's a funny thing about this correlation energy definition. But the physical meaning, as I said, is that if it is not small, then it means the electron-electron interaction term should be handled more seriously than reducing the problem to effective single electron problems. Okay, so that gives us an idea about why there is a research area called strongly correlated electron systems. For example, the high temperature superconductor, the quantum Hall effect things, and a lot of recent years condensed matter physics system, they are called strongly correlated electron systems. By that we mean our approach is not sufficient. We need to go further. The techniques involved in this area has to do with two-body Green's function that can be calculated by Feynman diagrams. Therefore, it is related to quantum field theory applied to solid-state systems, quantum statistical mechanics, etc. Okay, so these 2 pages, I just would like to introduce 2 concepts. Correlation energy is the difference between the best you can do within our level of approximation with the real value. Then, if this thing is not small, opens up a research area called strongly correlated electron system. Next, that answers some questions posted earlier today. How about the excited state, say 2s state of helium? Or lithium atom, what to do, right? So lithium, you may think, I need 3 functions, right? 1s lithium in one electron in there, another electron also in 1s, so 2 but identical, and then I need a 2s. That's true. Then you need to write down, focusing on 1 electron, what the 2 other electrons do in providing the effective potential, okay? Now what happens if I want the 2s excited atomic states of helium? Then I have to go to excited state of helium atom. Now roughly, a rough discussion here, I make a claim, my equation are not 100% accurate, okay? For some reason that we haven't mentioned yet. In the next set of notes, you know the reason, okay? So stay tuned. But at least conceptually, we can think through the idea. So roughly speaking, we may think that 1 electron will be with 1s, which is unknown. Another electron should be promoted to 2s because we are thinking about excited state. So this is also an unknown. Therefore, this time we have 2 unknowns, wave functions, right? But if we just think physically, we focus on this electron in 1s. The second electron in 2s must be producing a potential like this, acting on number 1. It itself is in 2s, which is also an unknown. If we think about the other electron in 2s, then the other one will be in 1s, producing such a potential energy function on 2. All right. Now you look at this. This is a set of 2 coupled equations that you need to solve for 2 unknown functions and 2 unknown energies. But that can be done self-consistently. You guess 2 inputs, then you can calculate this and that. You will get 2 outputs. You compare the 2 inputs with 2 outputs, loop it again and again. That can be done. All right, so that is the idea, okay? So bigger atoms, no problem. We have this idea of setting up a set of equations. But here I hinted at something that I am not 100% accurate for the reason. Footnote here is that I have 2 electrons, but they are identical. I cannot distinguish one from another. Every properties are the same, okay? And that has some role to play in setting up the self-consistent equations. That will make my equation, I miss out 1 term, that's to say, okay? And what is the term that I missed out? Now look at all this term. There are 2 wave functions here, square, right? And then a 3rd one, so 3 wave functions. Now, what if I have such a funny term? 3 wave functions, okay? It is an operator, all right, because it is waiting for something to come in, all right? This 1s, but this is 2s. There's no classical interpretation to operate. You come in, I do the integral. You come in, I do the integral, okay? So when we look at the indistinguishability of the 2 electrons, then this kind of term will come in as an extra term here. I still have another term, and that is called the fork term, but still you have 2 equations to iterate. Therefore, that theory will be called Hartree-Fock approximation. I mentioned this term before last time. This is called the indirect Coulomb term, or simply called the exchange energy term. So With this idea in mind, for other atoms, we can repeat this calculation for every single atom and get the 1s, 2s, 2p for the many atoms. All right, that has been done. Here, I give you a small table, you can blow it up by yourself, okay? Here, I list the different elements, you see, the different atoms, okay? And it is the ground state. So therefore, for helium, I only have the 1s, and the best Hartree value, I use this independent particle approximation, is this 0.8605 Hartree. This comes again to the point that take some time to read the 4 pages of appendix on the atomic unit. You see, these values are all cited in Hartree. That is the commonly used units in atomic and molecular physics. It is 2 times 13.6, all right? With a minus sign. Okay, so now for lithium, the ground state has to do with 1s and 2s, thereby a set of equation can be set up to loop to do this self-consistent calculation. The best values are that, okay? If you think about the atomic state, you can think about it as minus 2.199 Hartree lower, okay? 1s, then this is minus 0.2 Hartree, that is higher, okay? And then everything here, for example, carbon, there are 3 atomic state, single electron state involved, 1s, 2s, 2p. And these are the best values. Okay, so now I hope at least you see, when you see this table, first of all, you know what the numbers are about. Secondly, you appreciate the quantum mechanics behind such a table. All right. Once upon a time, when you study chemistry in secondary school or general chem in university, you might think that easy, everything is like this. Okay, now you see, even helium, the number 2s was not given here. Because if you want to do that, it's a different calculation and it's not the ground state, it is the excited state. You have to do it again. Okay? And here, now give us a sense of, now we still have to discuss how to fill the electrons in, okay? But I hope that you, at least you know the Pauli exclusion principle, all right? So therefore, you have this so-called electron configuration of the ground state. Helium, you put 2 electrons into 1s, you have this funny symbol 1s with a superscript 2, all right? And here's the term symbol, something that we already discussed. It is referring to the ground state. So the orbital angular momentum is S, L equals 0, but we use a capital S, okay? And then this ground state, all right, is a spin singlet, all right? And then J is 0. So we have this term symbol. And then we have all these electronic configurations. Many times you see this lazy way. That means a core of helium structure is here. So it's 1s, 2s, okay? But be lazy, then don't write it at all. So sodium, formally it should be 1s, 2s, 2p6, things like that, all right? And then 3s1. But then this is a neon, so that already have all the other things in front, okay? Finally, you may wonder why we are doing all this. There's no calculation that we can do, right? You need to write a program. We are not doing computational physics, then we cannot do anything. But I think culturally, educationally, conceptually, they are valuable. First of all, in this discussion, you get some ideas of how many electron systems are treated, right? How, at least, how on Earth it is possible to reduce many electron problems to single electron calculations. But we now know that can be done, but that is not easily done. A lot of complicated thing, self-consistency. Secondly, computational quantum chem and computational material science is now a very popular research area. In our department, we also have teachers doing computational material science, for example, Professor Zhu Zhenyi. So sometimes he uses some big packages, density functional, sometimes maybe Hartree-Fock. At least conceptually, you know how involved those calculations are. Or some of you may decide, I like this, I will go into this field. Good for you. Also, there are numerical packages to do it for you. But if you have money, that doesn't mean anything. You buy the package, you don't know what this menu is about. You pull down a menu, there are different methods. You have to choose the methods. At least you have some idea what the methods are doing, right? I already mentioned this company producing the most popular product. And it is the beginning of many-body physics. In many-body physics, what we did about Hartree is one Feynman diagram. What we talk about the exchange energy, the Hartree-Fock is another Feynman diagram. But if it is a strongly correlated system, don't stop there. You do more Feynman diagram calculations. So that is the beginning of many-body physics. Okay, and then I think that will back you up from some misunderstanding or oversimplification of what you learn in chemistry course in high school and in your year 1 chemistry course. The main message is that basically all of chemistry is quantum physics. It is not my statement. It is Dirac's statement. And more, how about nuclear physics? Believe me or not, we already did some nuclear physics in our discussion. So what is a nucleus? Nucleus is something of the size 10 to the minus 14 meter to 10 to the minus 15 meter. Okay, from the periodic table, you have thousands of nucleus because they are isotopes. Some bigger, some smaller, off by 1 order of magnitude. Okay, because the smallest will be 1 proton, the biggest one will be a few hundred, maybe 200 something proton and neutrons in a plutonium nucleus, for example. Okay, so here in a cartoon way, I use some black dots for neutrons, I use some crosses for protons. This collectively are called nucleons, okay, and they interact between themselves through nuclear force. Strictly speaking, in the particle physics language, it is strong interaction. But we are doing nuclear physics discussion here, so it is a short-range nuclear force. In addition to that, proton-proton, the crosses, of course, they are positively charged, they have Coulomb repulsion as well. So proton will interact through 2 ways. Coulomb and nuclear force, but neutron only interact with all the other neutron and proton through nuclear force. In nuclear physics, the most important approximation is nothing more than independent particle approximation. What does it mean? If we focus on a neutron, all the other proton and neutron are responsible for producing an effective potential energy term into a single neutron Schrödinger equation. After we do that, we have single neutron states. Then we use Pauli exclusion principle to fill in the neutrons. Because neutrons are spin half, they also obey the fermion or electron Pauli exclusion principle. So we are done with neutron, but the complication is we have to do the proton question again. We focus on the proton, the other neutron and proton will provide another effective single proton potential. But this time, this will be very different, well, slightly different from that, because proton can interact two ways: nuclear force plus Coulomb repulsion from the other protons. Thereby, the V effective into the Schrödinger equation in proton will be different from neutron. Nonetheless, it's a single proton problem. You fill it in, fill protons in, then you have the neutron, proton, how to fill it up, okay? After that, you can explain a lot of phenomena. Why a nucleus don't want to have so many protons, and it will do decay, beta plus decay. And when the nucleus has so many neutrons, it will do beta decay, okay? So you can imagine filling up the proton up to here in energy, blowing up the neutron up to here in energy. Suddenly this is higher than the other side. There are state for protons here. Why not do some decay and then go to this side to lower the nucleus energy? When it does, it is beta decay. Okay, so this simple independent particle approximation actually is a very powerful approach in many different areas. And some Nobel Prizes in nuclear physics were awarded within this picture, Koshel model. Another reason why I make this discussion is that there are some big names that you should know. In this self-consistent calculation approach, Nobel Prizes in chemistry have been awarded to John Pople and also Walter Kohn. Walter Kohn is a physicist in training entirely, and he also made fundamental contribution to a big area called density functional theory. Now it's the most popular method in calculating electronic band structure in semiconductors and many other solids. Another guy who did a lot of this kind of quantum theory of atoms, molecules, and solid is called John Slater. Next part, you will see his name again in writing down many electron wave functions. It's called Slater determinant. But he did a lot of things on the topics that we discussed here. Basically, simply put, he built up MIT's physics department's reputation to the status it is now. He was the department head for a long, long time at MIT. And he wrote many books. You go to the library, look up his book on the quantum theory of atoms, molecules, and solids. you will find several books written by him from 1940 to 1970. They are all classics now. Okay, so for those of you who want to know more, I cannot tell you any more in this course. Okay, we have to go to other topics, but there's some further reading. You can look it up. This quantum chemistry book has a chapter even telling you how to use the Gaussian program. And then I mentioned this book as this is an undergraduate level computational physics textbook. Nicely, it gives you a program for the helium atom ground state problem. I think you can even borrow a disk with the program inside in the library. And this introductory article in the journal, American Journal of Physics, is very readable, even for undergraduates. It gives you the variational calculation approach in getting at the Hartree and Hartree-Fock calculation equations. So I have been using hand-waving method, physical sense, in writing down this self-consistent equation. But in fact, you can start from basic, our trial wave function, vary the whole function that is called functional derivative. Then you can get this self-consistent Schrödinger-like equation mathematically, but the same equation, of course, okay? And it is a very good place to get a sense of how the formulation can be established mathematically, okay? So I think I have to stop here. Next time, we will do the symmetry of many electron wave function. It's a big bit of knowledge. The answer is very simple. There's no proof, okay? Nature tells us that many electron wave function must be off by one sign. Plus becomes minus, minus becomes plus when we interchange two electrons in the wave function. That's it. That is an overarching principle in which the Pauli exclusion principle comes out as a byproduct. So we will do this discussion next time. Then we are done. We have all the states that we can get using independent particle approximation. Next time we know how to fill in the electrons. Then we are done with all the atoms and molecules, more or less the same basic ideas. Okay, so I will stop here and then I will stay around to answer some questions.